Lots of people struggled with question 33 for a couple of key reasons. Firstly, it's a piecewise function, and some people found that confusing. But a piecewise function really just says, look, in different parts of the domain, there's a slightly different rule governing y equals f of x and the shape of the curve there. So you've got to draw a different sort of graph in each section. Now, the other reason that people found it hard is because they tried to integrate each section to find the value of this definite integral. And the trick is that we haven't actually learnt the rules to integrate something like this that's inside a surd. So you need another method. Now, the easiest thing to do, I think, is just to sketch the function, because then you can see what the shapes are. This question is actually testing your understanding. Do you realize that when you find the value of a definite integral, it is related to the area between the curve and the x-axis? So if you have found the area, you can reason what the definite integral is, and if you found the definite integral, you can reason what the area is. The third thing that it's testing, other than just do you understand piecewise functions, do you know how to get around this problem without being able to integrate it, it's also testing, do you know what to do about areas that are underneath the x-axis? Because they'll have a negative value as a definite integral, but they'll have a positive value as an area. So graphing this thing from 0 to 2, it looks like this. Now, I already know that this curve here is a semicircle. And I know that because if I squared both sides, I'd be changing it a little. I need to acknowledge that this is just y being always positive. But if I squared it on both sides, then I would have this, and I can rearrange that to look a lot like a circle with a radius of 2. Now, this one's not a circle with a radius of 2, it's a semicircle. I squared it to see the circle that it was like, but importantly, it's just the top half of the circle. And in fact, I need to only draw it from here to here. It has a radius of 0, so it's going to be a quarter of a circle like that. That bit's done. All right, this section is just the line y equals x plus 2. Now, that's got a gradient of 1 and a y-intercept of 2. So it exists between -4 and 0. So between here and here, I need it to go through here and have a gradient of 1. Well, a gradient of 1 means it's going to come down here through this point, and by the time it's down here at x equals -4, it's going to be lining up with the -2, isn't it? So it's down there. All right, for the bottom section, anything less than x being -4, it's just a value of -2. So it just goes along like that, level with the -2. So that's my graph. It goes on like that forever, goes up there, and then finishes. That's it. So if I want to find the value of the definite integral between -6, that's here, and here, then if I can find the value of each part and reason which ones are negative, these bits, and which ones are positive, then I can just add my parts together. So my working will say from -6 up to 2, the definite integral is going to be equal to, now, there's lots of ways you could set this out. You could say, look, let's divide these into sections. A perfectly acceptable way to do it would be to call this part A. This part here could be B. This part here can be C. And this part here could be D. And if you've got a graph there in your working and you've labelled it like that, then you can use your labels in your working. Now, A and B are going to be negative. C and D are going to be positive. So I'm going to need C and D. And then I'm going to need to subtract A and B because they're going to be negative. And you can put these in any order. I could have put -A plus -B plus C plus D. Now, B and C are both triangles with a base of 2 and a height of 2. So they're going to be the exact same size. So if you want to, you could even discount them from the start and explain these are the same size. Therefore, we don't really need to include them because we've got C and then we're taking away B. So really we just need to find D minus A. All right, the area of D, well, that's a quarter of a circle. So a quarter pi r squared, where r is 2. and we need to subtract a. A is just a rectangle. It's got a height of 2 and a base of 2. So it's 2 times 2, and I've deliberately put that in there rather than put 4, so it's really clear how I calculated this. So I've got 4 quarters, which is 1, that just gives me pi, minus 4. And that is the value of my definite integral. Now we don't want to put units square. We have not actually found the area underneath the curve, or between the curve and the x-axis, between these bounds. That would be to add together the absolute value of a and b with the absolute value, they're already positive, of c and d. And we haven't actually done that. What we've done is acknowledge that some of the areas are going to be below the x-axis, so they actually have a negative value as a definite integral. Now, if you didn't draw it and you just tried to find your definite integral by breaking it up into the different parts, then there's a few things you'd need to do. You need to make sure that you've got the right bounds for each section and the right part with the right bound. These two parts are quite straightforward to integrate. Still more work, I think, than the method that we used before. This first part will be x squared over 2 plus 2x, and all of that between these bounds. And this section will be negative 2x, or you can bring your negative 2 out the front, and we've got our bounds in there. Then subbing in our bounds, we've got 0, which helps as a placeholder because we know we need to subtract now. When we sub in the negative 4, we get 16 over 2, so we have 8 plus, now putting this part in brackets is really helpful. No, not plus, we have minus. Now, we've got 8 minus 8 there, which is 0. 0 minus 0 is 0. So that whole section worked out as 0. Does that make sense from what we know? Yeah, that's the two sections that we just looked at, B and C. They're going to cancel each other out. And if you did it this way, you should find that still. And this section over here, we've got, what do we get here? 8 minus 12. So that gives us minus 4. So this section here we haven't accounted for, but the other bit's the minus 4, which we actually found using our other method. It's effectively just that little rectangle on the far left side of our graph. This bit here, you're probably going to be tempted to have a look at it with this, but we haven't actually got any rules for reversing the chain rule here. And that's because if we've got some function and it's raised to some power, normally we can integrate that only if what's out the front is f dash x. And we don't have minus 2x, or in fact any x's out the front here. If we had an x here and it wasn't minus 2x, we could make up for the constant by just dividing by a constant in our integral. But we don't have any x's there, and so we don't have the rules in this course to integrate that. So we need to be able to reason that it's a quarter of a circle to figure out that the area of that section is pi, so the value of the definite integral for that section is also pi.